Now, we finally arrived at spherical polar coordinates, the last standard coordinate system. Here, this coordinate system is important when you deal with spheres or portion of spheres, right. We will see how we apply spherical polar coordinates in such situations when we arrive at examples. All right. Now, we will consider a sphere centered at the origin. Now, take a point on the sphere, let that point be P. Now, the distance from O to P can be taken as R, and now OP is a line segment. The line segment makes an angle with the positive direction of Z. Now, let this angle be phi. Okay. Now, we project OP onto xy plane. So, like this, and the projection will be OQ, right. Now, this angle, the angle between OQ and the positive direction of x axis can be taken as theta, right. Now, from this diagram you can see that if this is R and if this is phi, right, this angle between the angle between OP and OQ is 90 minus phi, because Z axis and OQ are mutually perpendicular. Therefore, if this angle is phi, the angle between OP and OQ will be 90 minus phi. Therefore, this length OQ is R sin phi, as I indicated there. It is R sin phi. Now, after that, once you project OP onto xy plane, the projection will be OQ. Now, again you project OQ onto x axis, and similarly you project OQ onto y axis. Now, this will be, since this angle is theta, OX is OQ cos theta, like this. And since we know what OQ is, you plug in R sin phi for OQ and you will end up with this one. And then OY, again you project it onto this one, this angle is 90 minus theta, therefore, this is OQ sin theta. OY is OQ sin theta. Again you plug in the expression we obtained for OQ, then you will end up with this one. And it is a piece of cake to find OZ. It is simply this, since this angle is theta, this is R cos phi. Okay. Now, we need to look at two things. First is how this forms a rectangular coordinate system. Second, what is the infinitesimal volume element of this coordinate system, because we need that to evaluate integrals associated with this system, right. Okay, we will move to the next one. Again, again I want to tell you that in this case this curve is, in fact, if you take this as a globe, this curve is a longitude. Likewise, in this case, this is a longitude. Now, let this point be P. I have forgotten to indicate that, even though it is not necessary, let us take it as P. Now, the line segment which connects O and P is of length R, right. And therefore, to increase R, to increase the distance between O and P, you have to move along this direction. That vector can be taken, that direction can be, the unit vector along that direction can be taken as R hat. Now, if you take phi, to increase phi, you have to move along that longitude this way. So, to increase phi, you have to move along this direction. the unit vector along this direction can be taken as phi hat, that is this. Now, finally, once you project this point P onto Q, which is on xy plane, to increase theta, theta is this angle, to increase theta, you have to move along this circle this way on xy plane. Therefore, it is if I without changing, in fact, this is theta hat, without changing this vector, without changing the direction and the size, you can take this up there. Now, this is where you have r hat, phi hat and theta hat. Now, if you look at this diagram, you have them in this, you have this orientation. And if you take xyz coordinate system, you have it in this way. When you take a screwdriver and move it in this direction, the head moves along this direction. Head moves along the third coordinate axis. Similarly here, if you take r and phi, look, we have to rotate the screwdriver like this, like this. Then the head moves inside along theta hat direction. That means r hat, phi hat and theta hat form a right hand coordinate system, those directions. Therefore, we write it like this: r, phi and theta. It is a r, phi, theta coordinate system. R is the first coordinate, phi is the second, theta is the third. Like you have the similar orientation. Like here in the place of, I mean, here it's rotated, but right, because you might see that r hat is in the direction of z. Yes, in this diagram it looks like that, but if you take this as the first coordinate, if you assume that this is the second, and if you take a screwdriver and rotate it in this direction, the head moves in the direction of theta hat. Therefore, the first coordinate, this is the second coordinate, this theta is the third coordinate. Now, just, I mean, to solve problems you don't need this, but to understand the coordinate system you need that orientation. Now, we will move to the next one, that is infinitesimal volume element. You need that almost all the time when you deal with some evaluation of an integral using this coordinate system. Now, this little tricky, but you have to pay attention to that. Now, again, let this be this point be P, and the distance between O and P be R. Now, to increase R, to give a infinitesimal increment to R, that is delta R, you have to do it in this way, right? So, this line segment is delta R. Now, to increase phi, if you increase phi a little bit, that is delta phi, then this is the result of that increment. What is this length? This length is, okay, this is the radius is R, the angle associated with this, with this arc length is delta phi. Therefore, the arc length is R delta phi. Here, this length is R delta phi. This delta R. Those two are not very difficult, but the last one is little tricky. Now, once you project this onto xy plane, this where you have OQ. So, the angle between OQ and the x axis is theta. Now, if you want to give a little increment to that increment should be delta theta. So, the rotation will be like this. So, what is this length? That is little tricky. Look, length of OQ, you move along along the circumference of a circle. The radius of the circle is given by OQ, because to increase theta, you have to move along xy plane, right? Therefore, the radius of this, after the projection, the length of OQ, we saw it earlier, it is r sin phi. Therefore, the radius of this circle is r sin phi. The angle associated with this arc is delta theta, because we give a infinitesimal increment to theta. Therefore, radius is r sin phi, angle is delta theta. Therefore, this arc length is r sin phi delta theta, radius times the angle. Now, that is this arc length. If you take this up there, that is this one. So, this delta r, this is r delta phi, this length is, I did not indicate this because you know it will complicate the things. This one is r sin phi delta theta, this arc length. Therefore, now when delta r, delta theta and delta phi all go to 0, this becomes a cuboid. With this setup, it is not a cuboid because you have certain curves like edges, but once delta r, delta theta and delta phi go to 0, you do not have that. You have a perfect cuboid kind of thing. Therefore, you have a shape like this. This is delta r. As I explained you, this is r delta phi because that is this arc length. This arc length. This arc length was obtained here on the xy plane. Then we projected it up there. So, this is we saw this as r sin phi delta theta. So, this is r sin phi delta theta. Now, the volume should be the product of these sides. So, the volume of the infinitesimal element is delta r times r delta phi times this one, r sin phi delta theta. Now, you can gather these terms and you will end up with this one. Now, when delta r, delta phi and delta theta all go to 0, you can replace these guys by dr, d phi, d theta. So, you will end up with this one. So, this is the infinitesimal volume element in the case of the spherical polar coordinates. Now, if you want to deal with some kind of an integration, like in xy z plane, you take it as dx, dy, dz. Probably in cylindrical polar coordinates, you get rho, d rho, d theta, dz. Similarly, here you have this additional factor. This probably out of all these coordinate systems, this is the most complicated one. You have like r squared sin phi as that scale factor. We will see what it is later when we discuss the Jacobian. Now, this is the infinitesimal volume element. So, no matter what it is, when you integrate something in a volume, you always have to take the in the integrand, you need to have r squared sin phi dr d theta, sorry, dr d phi d theta as your infinitesimal volume element, right? Okay. Now, after this, we need to go through some examples to see how we evaluate certain integrals inside spheres or inside a portion of spheres. When we deal with those problems, we always have to take this as your infinitesimal volume element. Okay, thank you.